Okay, good afternoon, everyone. Good afternoon. Good afternoon. So your midterm 1 is officially closed for the entire class. Okay, as I mentioned in the last lecture, I will have your exams graded by the end of fall break, and then we will have it returned to you on the Monday after you come back from fall break. Okay? Alright, so for today, we're going to continue with first order system response. It looks like I'm still getting an echo of some sort. People in the back, can you hear me still? Okay, alright. So we're going to continue with first order system response, and we did the math last time. We would like to have an example that kind of reinforces this idea. Okay? So we will take a look at a very practical example, which is the human body. All right. So I'm a human. I stand in front of you with my arms tucked. You can more or less think of me as a cylinder, isn't it? So we're going to say that an actual physical human body, which is a very complicated creature, can be modeled in the form of a cylinder. Okay? So actual system. This is the physical system. Now we have a system model for this. Right? The height of the cylinder could be the height of the person. The radius or the diameter of the cylinder could be the circumferential dimensions of the person. One of the foundational characteristics of a human body is its temperature. Right? And temperature typically is a function of space and a function of time. Which means that if I have an XYZ coordinate system, so in general, let's say T is temperature, so T is a function of x, y, z, or r, theta, z, whatever coordinate system you want to choose. It's also a function of time, little t. But under a special set of circumstances, which we will learn towards the end of this course, which is called as the Biot criterion. Okay? So under certain special circumstances, under certain restrictions, this is called as the Biot criterion after the French physicist Maurice Biot, a very seminal figure in mechanics. The Biot criterion, or the lump parameter criterion. Okay? We can assume that temperature is a function of only time. Okay, so this will tell us temperature is a function only of time. Okay, so with that said, what we will say is, okay, there is this human person who is standing here, and they're going to be modeled in the form of a cylinder, and rather than have the temperature be a function of multiple variables, so that the governing equations will be a partial differential equation, you restrict the problem under this Biot criterion, which we will learn towards the end of this semester, and you have temperature as a function only of time. Okay, so now T is a function only of time. So what would we like to do? You are sitting in this room, nice and toasty. You are at a nice comfortable temperature. Your core is at 37 degrees Celsius, more or less. I'll convert that into Kelvin or Fahrenheit, whatever you want. The minute you step outside, where it is much colder than what it is inside here, and obviously the outside temperature is lower than your body temperature, what's going to happen? You're going to lose heat. Right? So which means that the temperature of the body is changing as a function of time, and we want to understand this by means of a system dynamics model. That's our idea here. Okay? Complicated thing, the human body. You make use of some criteria, you make use of some adjustments, and then you say, okay, this is this lump here, lump of clay, whatever you want to call it. The temperature is no longer a function of space, it's a function of time only, and here is what I want to do. I want to understand how this is characterized into a system model in the form of a differential equation. Okay? So look at this. Let's say that the minute you stand outside is when time begins. So t is equal to 0. So at that point in time, right as you stand outside the hall, or outside this room, or outside this building probably, your temperature is going to start dropping down, because we are assuming that your temperature is higher than the surroundings to begin with. I'm going to call the surroundings as having a temperature T infinity. Okay, so T of T is the temperature of the body. T infinity is the surrounding temperature or the ambient temperature. Let's say that the temperature of the person at T is equal to 0 is some T naught. Okay. Say is T naught, and because it is winter, we will assume that this is greater than the surrounding temperature. If it is summer, you just assume the opposite. Right? Now we want to construct a system model. Okay? That is, how do we use this caricature of a human being and then come up with an equation, a mathematical equation. And here is how you do it. You make use of the first law of thermodynamics. You're taking 3501, you know the first law, right? So using the first law, which is the physical principle that is applied in this problem, we previously used to use Newtonian mechanics to come up with the equations of motion. Now we are using a different set of fundamental laws. You can say the following. I will write this down first and then explain the terms. The rate of energy transfer into the system in the form of heat transfer or work transfer subtracted from the rate of energy transfer out of the system is equal to the rate of change of the stored energy within the system. This is the foundational first law of thermodynamics, as you know it from 3501, right? And in some sense, you don't need the rate form. You could also write it in a change form. Delta E in minus delta E out is equal to delta E stored, right? So I'll just write that down. So this is rate of energy transfer into system. This is the rate of energy transfer out of the system. This is the rate of change of stored energy. The same equation you're going to see the last couple of lectures in the semester being repeated. Okay? We are actually doing thermal systems now. But I want to motivate all the math that we did last class by means of an actual physical example. Okay? Alright, so if that is the case, here is my system. The system is a body, right? So what do you do in thermodynamics? You draw a control surface, you identify a control volume, right? You do something similar. Intuitively speaking, what do you think is going to happen? Is there going to be energy transfer into the system or energy transfer out of the system? Most probably out of the system, right? Because you're starting off at a higher temperature to begin with, so you're going to give out some heat, right? So there is going to be some dE out by dt. There is no dE in by dt in the system that we are considering, okay? So if I look at the equations, dE out and as you go into heat transfer, which you will probably take during your senior year, you will see that the transfer of heat between a solid body across the interface with a fluid body takes place by convection heat transfer. Okay? Convection heat transfer is typically given by some constant value multiplied by the temperature difference. So this is some constant C1 times the temperature difference between the body and the surroundings. Okay? This is something you're just going to take it as a matter of faith. Okay? This is convection heat transfer. So heat transfer from the body to surroundings by convection heat transfer. You know the three modes of heat transfer: conduction, convection, and radiation. Don't worry about what they physically imply and so on. We are just using them as equations in this sense. All right. You also know from thermodynamics, hopefully, that E stored is the mass of the system times the specific heat capacity multiplied by a temperature difference. Right. So this is a mass. Specific heat typically at constant pressure is what is used. Okay, multiplied by the temperature difference. You can choose any temperature as a reference temperature. The reference temperature is an arbitrary choice. Okay, so this is typically a reference temperature. You can choose anything because it really doesn't matter, as long as it's a standard temperature. You can choose 0 as your reference for all you get. If I take the derivative of that, the only thing that changes as a function of time is T of t. Is n times Cp times. Does this make sense to everybody? You have this person, the person is hot or generally hotter to begin with than the surroundings, and then what's going to happen is there's going to be some heat loss taking place. Because of the heat loss taking place from the person to the surroundings, the amount of energy stored within the person is also going to fall down. Right? So what happens, the consequence is maybe dehydration in some sense, or some kind of a hypothermia in some other sense. Right? So these are the consequences of this action here. Hypothermia probably here, because what do you think intuitively is going to happen? I'm going to keep on giving heat to the surroundings until my temperature is the same as the surroundings. That's not a good idea, but this is what the problem will tell you. Intuitively speaking, this is the behavior you expect. Can I bring about it mathematically, which is what we're doing here? Okay. So if I rewrite my equation, dE in by dt don't need to rewrite it, you already have it there. dE in is 0. There is no energy entering the system. You have some energy leaving the system, and so if you substitute for all of these, I have some constant this is equal to or if I rearrange things, I'm going to write it two ways. Okay, so look at this. First way, I'm just going to bring that term onto the other side. MCP and this is the temperature of the body at the beginning of time. This was purportedly larger than T infinity. I perform the following change of variables. Okay, this is very common in heat transfer and in thermodynamics, typically as you go into the rate forms. So say theta of t, some variable, theta of t, okay, is the difference between the two. What do I have here? If I take the differentiation on both sides, d theta by dt is dt of t by dt. T infinity is a constant temperature, so that does not undergo any differentiation. So if I substitute, you see that this equation, if I rearrange the term C1 and bring it onto the other side, you see this takes a form and theta of 0 is theta naught, which is nothing but t at 0 minus t infinity. What form does it have? It has the same form as the standard form for a first order system. That first set of quantities, mc by constant and all these things, these are just called as tau. That's what we call them in the previous lecture. So this is just tau times some theta dot plus theta of t is equal to 0. What type of a response is this? There is no forcing, which means that this is going to be a free response. We have already performed the free response analysis, so I have a canned solution available. I can just employ that solution, throw it out and walk my way around. I don't need to think much, you see, because we already done the hard work here. I'm going to wait until everybody gets it, and I'm going to pull this back down. If I can find where the thing is. Is there? Yeah. Thank you. You get a bonus 5 points. Pointing that. All right, I'm going to pull this thing down. Yes, question?
Is there supposed to be the C constant in front of the theta term?
No, so I divided through that.
Oh, okay.
Right. And because the other side is a 0, so it does not affect it. Yes, question.
NCFD is just a constant for
Yeah, you just think of it as this entire thing is just some constant. It's typically, if you do thermodynamics, this is mass, this is specific heat due to constant pressure. Okay? But just think of it as a big big constant. Doesn't matter at all. Okay. And so that's one model that I have. And hang on. So we have some tau, theta dot, theta of t is 0. Theta of 0 is equal to theta naught. What is the response? We just pull out the solution. Please refer to my lecture notes from the previous class. We have solved this, and this is just theta naught e to the power minus t by tau. Tau is called the first order time constant, okay, which we have seen in the last class. On the other hand, if I rewrite the same equation from before, from the previous panel, but without the change of variables, so I have MCP I can do the following, okay? Divide through by C1, so that I have MCP I'm left with the T infinity, bring it onto the other side. This is T infinity times 1. If I want to write 1 as a function of time, what is the term I would employ? Unit step function. This is just T of infinity times U of T. And the initial condition was that. So you see, this problem is a special problem because it amends itself both to a free response type solution as well as a step input type solution. But we already solved this problem. I can employ the solution that we have obtained in the last class. And so T of t will be some T infinity U of t plus T naught minus T infinity. These are both the same. Okay, in this particular problem, these two solutions represent similar ideas, and we could have a plot. Likewise, a plot here. Instead of theta, I would call it as t. This is a free response, so it tells me a start at theta naught. Okay, and then what does it say? What is the steady state value of the system? The system is just going to asymptotically hit 0 as time goes on, a square.
Can you explain where you get the step function u of t?
Oh, yeah. So this is, you see, this is t infinity times 1, right? So u of t, by definition, is the following. So you see, instead of writing it as t infinity times 1, I would rather write it as this because I know the Laplace transform of that u of t is 1 by s. So it helps me in the solution process. That is the only reason why we would like to write it this way.
Would there ever be a case where you go into negative t as like a...
Oh, negative time, not in system dynamics, not in the dynamics that we do. You could have the full space of the solution, so the Laplace transform in reality is defined from minus infinity to plus infinity. We are using the right side of the Laplace transform. You see. Yes, question?
Is it 1 over s or 1 over s squared?
1 over s square is for the ramp function. Okay, we are going to come to that. This is 1 over s. Please check here. Okay, so I start off with theta naught, and the free response just decays down, as you can see, and we had a special value for the time constant at which the system appropriately reaches steady state, and that is 4 times the time constant. So when t is 4 times tau, the system is more or less at steady state. Any other decline in the system's value is not that appreciable. Okay, so this is approximately steady state value, which is 0 in this case. So the temperature difference reaches 0 between the temperature of the body and the temperature of the ambient. Or if you want a better interpretation of this, you can look at the step response here. I start off at T naught. I would eventually end at T infinity. I would be going down exponentially. And that would be steady state. So the idea I want to convey is this. You can look at it as pure mathematics. Okay, we have these differential equations, you solve them, but we are engineers at the end of the day. We are people who want to apply these ideas onto practical physical systems, and you see that there are endless applications that are amenable to this kind of an approximation. So I have a human body, which is a complex creature, but I can model it as a first order system. By tweaking it appropriately, it is also possible to model the human body as a second order system. I could model it as a third order system. If I reach an infinite number of orders, then I am obviously approaching the real behavior of the human body. The more number of orders I have, the more I am going towards the real behavior of that particular system. But sometimes it is not necessary. This is common sense. This is what intuition told me. Hey, if you're standing out in the cold, you better get dressed and hurry back in. Right? You're going to have your temperature fall down. This is just a no-brainer. The math tells you the same thing. So from now on, you can trust your intuition as well as the math. Okay? Does this make sense to everybody? You see the connection that we want to have between what we are doing and what physical systems tell us. Are there any questions so far? In some sense, this is a recap of what we did last class. We derived all these equation solutions. We derived this particular solution. This is an application of the solution to an actual physical problem. Question?
So for the forcing function in the problem, I see where you get the like right side, the t naught minus t infinity e to the negative t. With the forcing function, you can just kind of tack it on.
Absolutely, absolutely. That is the beauty of first order system. So if you look at a generic first order system, right, it's tau x dot plus x is equal to f of t. This f of t can be anything. The next example I'm going to consider f of t is going to be a ramp input. Tomorrow I'll come and say f of t is an impulse or it's a time delayed function. We're going to do delays in systems as well, which will lead to some kind of discontinuities and so on, but we will accomplish that next week. So that brings me to the next step that I want to go into. Question? Yes, very quick.
What's the difference between unit functions, ramp functions, and impulse functions?
We've gone through this and you're going to see it again. Okay, I want to motivate this by means of an actual physical example as well. Yeah. You've seen steel cables. I'm pretty sure all of you have seen steel cables, right? How do you manufacture steel cables? Is you take cylinders of steel and then you perform a heat treatment process. Okay? It is called an annealing process. So if you perform an annealing process on steel, it improves its workability. You can knead it. You can make it into a dough of some sort. You press the dough more and more, it increases its workability. You can make it into long, thin rods or sheets and whatnot, right? So this process of annealing is also something that we could model using the first law of thermodynamics and bring it into a first order system, okay? So here is the basic idea. You have a steel billet at some temperature T of T, okay? Let's assume that this temperature is a little more than the ambient temperature. You have ambient or surrounding temperature as well, which is T infinity. What you do in the annealing process is you first take this steel piece and you heat the hell out of that guy, okay? You take an external power source and you just keep increasing the magnitude of the heat that is supplied to it, okay? So let's say that the amount of heat that is supplied to it is in the form of a function of time. So it is some F naught times R of t. Okay, so now R of t is the ramp input, as we have described many times in class. This is 0 for time less than 0, and it is equal to the magnitude t for time greater than or equal to 0. This is a unit ramp. Why is it called a unit ramp? Is because its slope is equal to 1. If I multiply it by magnitude of F naught, its slope has been multiplied by magnitude of F naught. Okay? So this is the first step in the heat treatment process. So this is the heating. This typically occurs for a certain period of time. Okay, you don't want to heat this person all the time, right? Because then you'll just get a mush at the end of the day. So you go from 0 to some standard time T1. And the next step in an annealing process is you just let that fellow cool. Let that piece of steel chill. Okay? Which means that that person is going to lose heat. You heat it up first by using an external power source. Then you let that person chill. Why on earth am I doing these things? Is because if I do these things, the microstructure of the steel, of the grains, the carbon grains, they change. And the change in the microstructure brings about a transformation, a martensitic to a pearlite transformation, not important. It increases its workability. You can knead it much more better. Okay? So you do the next step, same thing. This is also a function of time, but now there is no external heating source, it's just surrounding. This is the cooling phase. From some time T1 all the way to some time T2. We've seen the cooling phase. The cooling phase leads to a first order free response or a first order step response, depending on how you model the problem. Okay? Now if I look at the heating phase, which is what my interest is today, because it is an application of a ramp input to the system, here is what happens. So I have dE in by dt. Okay, so this is essentially that character. This is dE in by dt. This is the rate of energy that is supplied into the system. Okay, dE in by dt, dE out by dt is dE stored by dt. You just substitute everything. dE in is some external power source which is supplying this heat, and that's a function of time. Okay, some F naught times R of T or something. Then do I have anything that is escaping? Obviously this steel person is getting heated up, so the temperature of the ambient surroundings is lower than this temperature, so there's going to be some heat transfer taking place in the form of convection, which we just discussed. Okay, so some C1 times, and this rate of change of stored energy within the steel body is just the mass times the specific heat due to constant pressure times the first derivative of the temperature. You can perform a change of variables and so on, and if you do that, if I bring this term onto the other side, I have perform the same change of variables as before. Some y of t, some variable, really doesn't matter what you want to call it. And obviously dt by dt is the same as dy by dt. And if I perform the substitutions, I bring C1 onto the other side and so on, I have mCp by C1 dy by dt plus y of t all the stuff mCp by C1, and if you look at the proper units of specific heat, mass and so on, it'll end up, and the units for C1, which is watts per Kelvin, we don't need to go into the details yet, but you will end up having units of time, which is seconds. Okay. Then I have this F naught by C1. I could call it by some other name. I'm going to call it as M naught. Okay. So this system equation essentially boils down to a standard first order system, which is tau times is equal to some M naught times R of T. I'm going to rewrite this once again in the next panel. So, with your permission, I'm going to pull this thing down in a minute, less than a minute. But this is pretty nifty, right? You have some actual process. This is very complicated. I mean, you look at the transformations of the microstructure taking place. There are things that happen that people still don't know anything about. Okay? But as an engineer, I can just sit here, use a back of the envelope calculation, and I can tell you, hey, this is going to be the temperature of the steel billet in 25 seconds. That is the beauty of what we're doing. Okay? I'll pull this panel down, if I can. All right. And I'll take questions in a minute or so after I'm done with my thoughts. And so my idea is now to study first order ramp response. Okay, so that is, I'm going to take the equation we ended up with, which is, for our convenience, I'm going to write here tau times y dot plus y is equal to m naught times r of t. R of t is the ramp function, u of t is the step function, okay? And initial conditions, y of 0 is equal to y naught. I would like to solve this system. How do I do this? I use Laplace transforms. Laplace transforms, once again, I want to let you know, is useful only for linear systems. If you have nonlinear systems, Laplace transform is no good. There are probably very few techniques that you can actually use for nonlinear systems. You have to use numerical methods. Okay? But the good thing is a lot of physical systems, however much complicated they are, can be modeled as linear systems. That's the point I want to convey here. You should take Laplace on both sides. Two or three standard functions, you always need to know the Laplace transform for. The step input or the step function is 1 by s. The ramp function is 1 by s square. The sinusoidal functions and the cosine functions, these are all things that I think you should spend some time and memorize those results. And make sure you remember them every day until at least this course is over. Okay? So Laplace on both sides, tau s times y of s, and then I have y of s again is m naught by s squared. Alright, so then I take the variables, I bring them onto the rightful places and so on. So I have tau s plus 1 y of s m naught by s square y naught, y of 0 is y naught. I have the characteristic polynomial of the system, tau s plus 1. If I look at the roots, s is equal to minus 1 by tau, and if tau is greater than 0, which is typically what it is for our systems, this is a stable system, right? So for tau greater than 0, the real part of the root is less than 0, so this is a stable system. And if I divide through by this characteristic polynomial on both sides, I get the following. Y of s is m naught s square times tau s plus 1. I'm going to take the tau as a common factor outside, plus y naught. I'm sorry, there is a tau that was missing there. That's tau times y naught. So this is tau y naught by, I took the tau as a common factor from the characteristic polynomial, which is why I write it in this form. Cancel these two. So y of s is m naught by tau s square s plus 1 by tau y naught by s plus 1 by tau. Alright, so I have the forced part of the response, I have the free part of the response. So y forced, I would write is m naught by tau s square s plus 1 by tau. S square is repeated in real roots because the roots are 0 and 0, right? And then I have s plus 1 by tau, that's a real distinct root. So you read the partial fraction decomposition as follows. So C1 s C2 s square some constant y1 plus tau. We've done enough partial decomposition of the fractions. I'm not going to go ahead and calculate all the C1, C2, C3. They are as follows. Okay, so C1 will end up as minus m naught tau. C2 will end up as m naught. C3 is plus m naught tau. Okay, if you perform the partial fraction decomposition and go through the process, hopefully, if you've been to recitation today, you will see that MATLAB is a really, really powerful option for solving these things. Tomorrow you might have a couple of recitation sessions as well. We're going to use MATLAB from now on. From next week onwards, it's just full throttle MATLAB. Okay? But I will be there to help. I will be there to go over it again in class. Alright, so if I do the substitutions, so y forced is minus m naught tau by s, m naught by s square, m naught tau by s plus 1 by tau. You take the Laplace inverse of all of these things, you get back into the time domain, which is where we want to be. Alright, so if I take the inverse Laplace, here is what happens, y forced. So take inverse Laplace. On both sides, so y forced. What is the inverse Laplace of 1 by s? The inverse Laplace of 1 by s is a step function. Right, so this is minus m naught times tau times u of t. Inverse Laplace of 1 by s square is nothing but the ramp function, right? So this is plus m naught times r of t. What is the inverse Laplace of 1 by s plus 1 by tau? E to the power minus t by tau. Plus m naught tau e to the power minus t by tau. I don't need to do the free response part of the solution because I already know it, you already know it, we've done it in the past. Y free would be y naught e to the power minus t by tau. So if I have a first order system, I have three things available to me. Free response, which is this particular person here. Then we had the step response of the system, which we had written in the past, right, at the beginning of the class. And lastly, I have the ramp response of the system, which is y forced as it is given here. We're going to write it in a much better form, okay? From next time onwards, if you see a ramp function, you don't need to do any Laplace transforms and inverse Laplace transforms. You just use this creature and go on your merry way, okay? Alright, so if I write yt, which is the combination of the two, watch this, minus m naught tau u of t. This creature I can write as the following. Does this make sense to everybody? R of t is nothing but time t, right? It's the value taken by time. When time is equal to 0, r of t is 0. When t is equal to 1, r of t is 1. When t is equal to infinity, r of t is infinity. It's multiplied by 1. I can always say 1 is the step function. I do this because I can combine this creature with that particular fellow. And so I end up with the following. It's going to be m naught times t minus tau. You can write the step function if you want. And then I have the combination of the rest of the terms, m naught tau e to the power minus t by tau, y naught e to the power minus t by tau. That becomes y naught m naught tau e to the power minus t by tau. Can somebody tell me what this decomposition means? What this term means and what this particular term means. What do you call that part of the response, the first box that I have drawn? What do you call the second part of the response, the second box I've drawn? Yes?
Steady state.
Fantastic. So this is steady state, right? And then you see that as time goes to infinity, this part of the response drops off. So this is going to be the transient part of the response. Okay? So this is y steady state, and this is y transient. And what I want to do is I want to sketch this response. I have 10 minutes left, so I'm going to do the sketching of this response, and we want to understand it qualitatively. And remember the example, or recall the example. What we were doing is we were taking a piece of steel, and then we were supplying an energy source. In some form, we were supplying heat into the steel piece so that its temperature increases as time progresses. That is the behavior you are expecting, right? Does the math tell you the physical intuition is right or not? We will see, okay? I'm going to pull the top panel down, if everybody is done with this. And the idea is that you learn these techniques, different types of techniques. We're going to do second order systems and so on. And you apply them in thoughtful ways. You see, you don't apply them just blindly to any kind of a problem. When you're dealing with a problem, you have to think, okay, does this have any global impact? Does this have any global challenges that it faces? Is there some sustainability component to that problem? Okay, is there some kind of an energy saving cause that this problem tries to address? You could model first order systems for population growth. That would address societal issues. Engineering issues, we are already addressing in this particular lecture. So you can use this for a gamut of applications. It is all up to your own interpretation of things. All right. I'm going to rewrite the response once again, with your permission. Y of t is m naught t minus tau u of t y naught e to the power minus t by tau. Okay. I want to plot this response. So look at it. T. This is some function f of t. I'm going to first plot the ramp input. Okay, so the input function m naught times r of t. R of t is a unit ramp, which means it is just a straight line passing through the origin with a slope of 1. But I multiplied by m naught, I am increasing its slope or decreasing its slope. I don't know what m naught is. Okay, it could be less than 1 to. This function is m naught r of t, its slope, that is tan theta, is m naught divided by 1, or the slope is m naught. If I plot this function, what do you think is going to happen? Let's say what's going to happen at time t is equal to 0. What's going to happen? What do you expect to happen at time t is equal to 0? Look at the function. Huh? It has to start from its initial condition. What else can it do, right? So it starts at some y naught. Absolutely. Thank you. What do you think it's going to do after this? It is going to slightly fall down a little bit. Okay? And why is that going to be the case is you can just substitute and see. When y is equal to 0, I get y naught. When y is equal to, let's say, 1 times tau, okay, what do I see is m naught, and then this is just going to be t minus tau, which is 0, plus y naught plus m naught tau e to the power minus 1. Okay? And if you plot it in the intermediate steps between 0 and 1 tau, if you take 0.5 tau and so on, you will have a negative component coming in. So this component is going to subtract from whatever else is here, and so this is going to fall down a little bit from its initial conditions. Okay? So it's going to take a slight swoop But then you see, I'm pumping in energy into the system. You remember the steel cylinder, right? I'm pumping in heat into the system. So the temperature of this guy has to pick up. So which means after some time, this plot is just going to start rising up again. Okay, it's going to follow the following plot. And what's going to happen at steady state, let's see. Okay, so at y is equal to 4 times tau, this is what might happen. It's m naught, 4 tau minus tau, plus y naught plus whatever that garbage is, e to the power minus 4. E to the power minus 4 is minuscule. It is 0.02. Okay, 0.0183 with a lot of other decimals, with a lot of other numbers. So that's very small, so I can more or less neglect it. Let me go one more time step ahead. Y at 5 times tau, m naught, 5 tau minus tau, plus something that is very small. Y naught plus m naught tau, e to the power minus 5. E to the power minus 5 is 0.006. It's also very small, very minuscule. Okay, compared to the previous terms. Its strength is not large enough. So what you're seeing is that as time increases, the slope of the response becomes the same as the slope of the input. Okay, see this. If I look at 4 tau and 5 tau. What is the value of the response at 4 tau? Okay, that is going to be something somewhat here. Or we can shift this guy down if you like. This is some value 3 m naught tau. Okay, that is the value of the response. That's the point that I'm looking at here. At t is equal to 5 times tau, look at the value of the response. Four times m naught times tau, right? You see, 4 tau minus tau is 3 tau, 5 tau minus tau is 4 tau. What is tau? Tau could be 1 second. I don't really care, it's a number, it's a time constant. But what I see is from one to another time, the magnitude has increased by the same amount. So if I look at the slope here, this difference is 4 m naught tau, 3 m naught tau, so that is just m naught tau. What is the difference between 5 tau and 4 tau? Hopefully 1 tau. So what is the slope there? If I call that as theta, okay, so this is the slope, theta, and theta is m naught tau divided by tau, which is m naught. So which tells me that once I go to steady state, this response is just going to keep following whatever the input response is trying to do. The input is just going to go to infinity. If I keep heating this up, I'm going to go beyond its melting point, recrystallization temperature, and all these kinds of things. I would just be left with a little bit of crystals there, which is not what my intentions are. I'm going to stop it at some point, but at steady state, this just keeps following the input. And this is a classical ramp response. Input, ramp, it looks like a ramp, that's why it's called a ramp. The output, it's exactly the same reason why it's called a ramp, okay? And the output, you see, it's dipping down, but because I am constantly supplying energy into the system, this guy has to pick up his bones and then move on, okay? And that is exactly what's going on. It is just going to go and start becoming parallel to the input, which is quite beautiful. And that is its steady state behavior. So at steady state, my last word for today, at steady state, y of t has same slope as m naught